Hello, my name is Jennifer Reiber Kyle, and I'm a member of the Developer Relations team here at Planet. And today, I'm going to talk about our project, which is crop type differentiation with temporal analysis and COGs. There's great promise in identifying crops from space. Crop inventory gives us a sense of the food security, and satellite imagery is quick and cheap. However, the issue is that many crops have similar spectral signatures, corn and soy being an example of that. And it's hard to differentiate them in one snapshot, no matter what sensor you use. Planet, however, has been building up a daily data set of the world. And so we wanted to do temporal analysis on that data set to see if we can come up with a temporal spectral signature that will help us identify the crops. This is just a small scale study to identify if it's possible to even differentiate the crops and build up a signature. And if it's possible, how difficult would it be to achieve? To study this, we compared ground truth data to imagery. The ground truth data that we used, it was collected in 2015 from a ground study. We had 3 different crop types that we looked at and 5 features from each, or 5 fields from each crop type. We used surface reflectance imagery, and it was collected in 2017 from between July and September, which is the growth season. And we randomly selected 50 scenes for each crop. This study was originally performed in 2017 using our first version of the Planet client. It used the top of atmosphere product, and it took about 2.5 hours to process the data set. We wanted to revisit the study to see if we could do any better. Here's the ground truth data that we used. You see it's centered around Sacramento, and it's pretty dense. We have about 1,000 features in this data set. Our selected sample size of 15 fields is shown on the right with the fields outlined. What we see here is a pretty sparsely located, and so we expect to have multiple scenes to collect all of the fields. The imagery we used is the surface reflectance product. We see the footprint of one of those images here on the left, and compare that footprint to the outline of one of those fields on the right. And one thing we can immediately see is we absolutely want to use COGs here and not download and process the entire image. Here's the data flow of our project. We have 3 major steps. The first one, we prepare the data set in a Jupyter notebook. That's analyzing the ground truth, filtering, sampling, and saving it. We then process the imagery for each field using Planet SDK for Python, as well as Rio Tyler for the COG access. So we activate and we only download the region covering the field. We calculate the statistics and then we save the statistics. And in the last step, we use a Jupyter notebook to visualize and combine all the data. Shown here is one of our results. This is the median value calculated across an entire field for one image. That's one data point. Beans are shown in blue, sunflowers in green, and corn in orange. Across the slide here, we have the surface reflectance of the blue, green, red, and near IR bands. And we also have the value of the calculated NDVI band. What we notice when we look at the blue, green, and red bands is that there is some difference in the surface reflectance, corn having less reflectance and sunflowers having more reflectance. There doesn't seem to be much of a trend over time. When we look at the NDVI, however, we see somewhat of a trend. Sunflowers, the NDVI value is going down over time. And for beans, it seems to be going up over time. And for corn, we have about almost 2 different data sets inside, one going down and the other one going up. One thing we notice is that it is pretty noisy data. And one potential reason for that is that we took the ground truth from 2015 and the imagery from 2017. And we do expect some rotating of crops over those 2 years. However, we do think that we found that there are some trends that are possible and it's worth looking into more. What we need to do is process more fields, and we need concurrent ground truth and imagery. We found that async improves the speed. We went from a processing time of about 2.5 hours down to less than an hour. It also adds complication. Rio Tyler is accessing the COGs using its own HTTP connections, and the Planet SDK is accessing, activating, and monitoring the imagery using its own async connections. And we found that there were conflicts unless we limited the number of processes that we were running. We limited to about 20, and that seemed to run just fine. The next step for us is to actually run this in parallel in the cloud using Lambda or Google Cloud Functions. This will allow us to analyze more fields and more images per field. We also want to redo this study with more recent ground truth. This will allow us to have the concurrent data sets and also allow us to make use of the better sensors that we now have on orbit. We also want to continue working on the Planet SDK for Python. This is the first real large-scale exercise of this tool, which is still in development. And we learned some things as well as being happy with the results. Thank you so much for listening to my talk today. You can follow along using these links to access the study from 2017, and in the future, the 2022 study will also be uploaded in the notebook repo. You can follow along in our development in the Planet SDK for Python, access a lot of great tools at the Planet Developer Center, or contact me directly. Thank you very much.